Okay, hello. So this is Lubos Breda, and thank you for watching this video. This will be a little bit of a webinar on the code, the source code behind Starfish. And so I'm hoping that since you're watching this, you're already somewhat familiar with what Starfish is. But in short, Starfish is this two-dimensional, and two-dimensional meaning either XY, Cartesian, or RZ, axisymmetric code for modeling, plasmas and kind of rarefied gases, and maybe also some, actual fluid flows. Okay, so it's kind of like a general tool for modeling, some kind of a gas, propagation, interaction with surfaces. Okay. Now there are two editions, as you probably know by now, and one I call, the light version or LE, and then there's the full version or the regular version. But the light edition is really the main code, is really the full code, and the full code is just the light edition extended with several different plugins. And you'll actually see in this seminar today what the plugins are and actually how you can extend the light version yourself with with some plugins. Okay. But kind of in short, the light edition is supposed to be kind of this, academic tool that, provides these kind of the basic functionality and allows you to learn about modeling, plasmas and rarefied gases. And the regular version kind of adds in some functionalities actually needed for more like, realistic problems, to actually, let's say, simulate some types of plasma thrusters and, stuff that is not, actually, publicly releasable. So that's the reason it's all separated in that way. Okay. So you can get the binary from this link right here, particleandcell.com/starfish, and you can get a source code which you'll need in order to basically start development from GitHub. So this is the link, github.com/particleandcell/starfish-LE. Okay. Now, on this website there's a link to this 5-step tutorial that shows you the kind of the basics of using the code as an end user. So it shows you how to actually set up the input files to run a simulation. And so I'm hoping, here that you're already familiar with that aspect of that, because I will not actually be discussing the, the input files. I'm just going to be going through the source code to kind of, because I'm, put here in this kind of bigger letters. In this webinar, I want to give you the basics that you need to start developing in Starfish. Okay. Now, a little bit of a plug here is that if you go on the website, you might also notice there's this other, there's a section about courses, and one of the things that I do, I offer these online courses on different topics relevant to plasma simulations and rarefied gas dynamic simulations. And so in 2016, I offered 3 courses. The first one was the fundamentals of the PIC method, and in this code we learned pretty much all there is to know about the electrostatic particle and cell method. So we started with 1D code, then we developed a 3D code, and we closed with a 2D axisymmetric code, and we learned about simulating sheets, about doing E-Crosby transport modeling, about modeling a flow of plasma past the charged sphere, and we developed kind of this simple ion gun example. And then the second course I offered was on distributed computing for plasma simulations. So this was a course about parallelization. So we learned about using multi-threading, then we learned about MPI, and we closed with learning about using about doing GPU computing with CUDA by basically using graphics cards to develop parallel codes. And the final course was the advanced PIC techniques, and in this course we covered kind of 3 main concepts. So the first one was that we studied the electromagnetic PIC, so the EM PIC, so we learned how to actually solve the magnetic field. Then we learned about direct simulation Monte Carlo method, or DSMC, for collision modeling, and we also learned about doing simulations on an unstructured tetrahedral mesh. So here we learn about solving the Poisson's equation using the finite element method, and we learn about pushing particles on this unstructured mesh. Okay. In 2017, I am not going to be offering these courses, at least not live. I will most likely re-record the lessons and just make the recordings available. But I plan on offering a new course on fluid modeling of plasmas, and in this course we'll discuss the MHD model, and also talk about smoothie particle hydrodynamics and volatile solvers in some some small level. Don't have a lot of details yet of the actual dates, but it will be offered sometime in the second half of 2017. So just basically keep an eye on the website for more information. Okay. All right. So going back to Starfish, this this schematic here kind of tries to summarize how the code works. And so what you have here in the middle is what I call a core module, and this is what provides the basic functionality. So this is some input-output stuff, for things like handling the input file loader, and also some of these base modules or base classes that are kind of used on later on. So the code contains a lot of modules, and these modules are things that are needed to implement a lot of this kind of physics that goes into simulating plasmas or or gas. But the modules that are kind of implemented here within this core are are meant to be very generic. So they don't actually go into a lot of the details of the physics. So they only kind of provide kind of the basic skeleton or the kind of skeletal framework that can then be used later on by some different actually detailed implementations that kind of flesh out the the code itself. So in more programming terms, here we have kind of defining some of the abstract or kind of the the base level classes that then need to be derived from or to be extended by some of these additional different packages. So the idea is that you might have let's say some a material type of a module defined here that just tells the code, hey, there are different types of materials. There might be it's just gonna have this kind of basic concept of a material, but then later on here I can basically we can define that I might want to have a material that's it's a kinetic material, or I might have a material is a fluid material, which will be updated or be governed by, let's say, the Navier-Stokes equations or diffusion equations, or maybe some pigment type of equations. And similarly, I might define here that I will have a solver module, something that's able to solve some kind of a TBD equation on the on a computational mesh, but it will not be later on until kind of the actual the meat is provided here that will implement different types of solvers, things like a Poisson solver or quasi-neutral solver, or maybe some exotic solvers that you'll come up with. And in the Starfish-LE code, some of these functionalities are already implemented. So the Starfish-LE basically contains all the functionality needed to run PIC, ES-PIC simulations with MCC. So the functionality for PIC, for MCC will be, it's already part of the Starfish-LE. But then what Starfish allows you to do, it lets you add these, more functionality using plugins, and we'll actually see on a future slide how these plugins work. But so, some of these things, like for instance, I mentioned here with the CFD or diffusion, this actually is not available in the light edition, but this is something that a plugin could provide, and this is actually, in fact, how the full version of Starfish works. So in the full version, I will have some plugins defined, and one of them will say there will be a material governed by the diffusion equation. Okay. Now, going back to the source code, to get started, you need to get it the same link that I mentioned earlier, and when you go on this GitHub website, you will see this option that you can either download a zip, or you can clone the the repo. So the main difference is that when you download a zip, you just get all the files and that's it. But when you clone it, you actually also get the version control information, which means that in the future, if I make some changes to the code and I update the version online, you can then easily get the changes kind of merge into your own version. So then Git will kind of compare your version that's sitting on your hard drive with the version coming in from this repo, and it will try to merge any differences. So this allows you to kind of retain any changes that you have made. So let's kind of put here some links. This is not, I'm not saying this is the best answer, but this is just one of the links I found just on Google, probably the first hit, but it just kind of gives out some basic information about checking out repos from from Git. So kind of maybe a good starting point. And there's also at least on Windows, there's a nice graphical user interface. It's called desktop, that you can kind of use to download stuff and run your own repo on your own on your own computer. Okay. Now, so once you have the source code downloaded, next thing you need to do is open it in some development environment, and the one I use is NetBeans. So NetBeans, it's one option. The other option that is commonly used is Eclipse. And I would imagine that you shouldn't have any problems using Eclipse instead of NetBeans, but NetBeans is what I use, so that's what we'll be showing here in these examples. So when you open it, you will have a list of packages that looks something like this. And so you can notice there's something called GUI. Ignore this. This doesn't work. I tried putting in a GUI and I just ran out of time, and I just spent a little bit of time on it, but didn't really get anywhere meaningful. So at some point in the future there will be a GUI, but for now it's just a console code. Then there's a package called main, and there's a bunch of these packages called starfish.core.something. Okay, and then there's starfish MCC, starfish.pic, and starfish.sources. Okay, so this is all the core stuff we talked about, and here is the basic functionality that is implemented in this light edition that allows you to run these ESPIC simulations with MCC. Okay. Now, Starfish, being a Java code, needs to have a main function, and this function can be defined anywhere in any class, but here I'm just defining in a class called main. I guess for whatever reason, which also happens to sit in a file called main.java. And you'll see that what this does is actually really short. It's just a single line command. But what we're doing, we're making a new instance of a class of type Starfish, so we're instantiating a new object of type Starfish. And once we do that, then we call a function in that object called start, and this function expects two arguments. The one is the kind of this this array of string that was passed into main, so these are the command line arguments. Okay, and the other one is is actually the list of plugins, and so in this case we have no plugins, so I'm just passing in a null pointer or null object into it. And I guess Java technically doesn't have pointers. Okay, so this is all it is. So next thing we'll do is we're going to take a look at this start method or function. And so you see, again, this is the signature right here. And so we'll kind of go through this now, kind of, line by line. But the first thing we do is we instantiate a new object of type logger module, and we save this into a, some variable, defined in this Starfish class or member variable, which is called logger_module. Okay, and there's another member variable that's not shown here, but it will be mentioned later, which is called modules. And so this modules is what's known as a map. So map allows you to map some kind of a key to a value. So here I'm basically mapping this log module to this string key called log. Okay, so I'm doing that, and you'll see in a minute why this is how this is used. But the reason we start off by instantiating this logger is because this is how all the different, how basically the whole code interacts with the user, how we actually print something to the screen. So, I don't use any, system out, printf commands. All the printing is done through this, log mechanism, this logger module. So this makes it easy because I can, print something to the screen, and it automatically also gets saved to a kind of like a log file. So, and there are also different sensitivity levels. So you have different messages. You can do like a log.debug, and it will only be shown if you're running in a debug mode, for instance. Okay. So next thing here is I kind of playing with a GUI. This would show the GUI, but again, this doesn't actually work. So this is just commented out. Then we just show the header, just print some copyright information to the screen. And next thing we call this function called register modules, and you will see this in a second, but this actually does something similar to this, where we just instantiate a whole bunch of different modules and put them into this modules map. Okay, and then if this plugins was provided, so if this is not null, then we iterate through all these plugins, and for each we call a register function. Okay. Next we initialize the module, so all these different modules that are created here in this register module, basically everything that exists within these modules, map will get initialized, and then we process the input file. So we load in the starfish.xml file, and then we exit the modules, which will just iterate through all the modules and call the exit function on them, and then finally we just show this message on the screen, just say done on the screen. So you can kind of notice that this is actually all that gets done. This is the main. This is what gets called by main. So this is really the when this finishes, this is the end of the code. Here we just terminate. And so you can see there is really no call to any kind of a main loop in here, and that is because that is actually done when we process in this XML file, when we encounter a tag called Starfish, then we'll call the process function for that for the Starfish module, which is what will then start the main loop. Okay. So going back to these modules data type, so this is how it's defined. So it's basically a map, but it's of a type linked hash map, but it's simply a map at the top level. So map is a type of a data structure that allows you to map a key, which in this case happens to be a string, to some other value, which happens to be of type command module. Okay, and this command module is a base class, is an abstract base class, and all these different modules that we are registering here are are some derivations, or basic extensions of that, or of that base class. They inherit from this base class. Okay, and so you see that in this register module, I'm just kind of putting in a whole bunch of different modules into this map. Okay, so things like node, boundaries, domain, and if you play with Starfish a little bit, you'll notice right away that these things you see here are actually the the commands that you put in your input file, in your XML file, and that's exactly what they are. Because when for instance, when the input file parser encounters tag called domain, it will call the process function on this on domain module. Okay. Now here's kind of just a quick overview of some of these different modules. I'm going to go through this really quickly. So node is a really simple one. It just simply writes some message to the log file, and it's kind of like maybe a good example, and we actually kind of see this in detail on the next slide. Boundaries is how we specify the the line segments that define the surface geometry. Since Starfish is a 2D code, then our surface is defined by lines or by some cubic splines. Domain is what generates the computational mesh or meshes. Okay, we can have multiple meshes, although the functionality is a little bit broken at this point, but will be fixed soon. Materials is how we load definitions of different solid or gas or fluid materials. Material interactions handles the different materials interacting with each other through things like chemistry or collisions, and it also handles a surface interaction, so particles interacting with surfaces. Sources is how mask is injected into a simulation, so this could be either from surface sources or from volume sources. Solvers are different field solvers, such as a Poisson solver. Output are functions for generating VTK or ParaV files. Time is how we control the time step size and also whether when the code should terminate. Load field lets you load in, let's say, external magnetic field. Restart allows you to to load or also to save restart data. This stop is kind of like a pretty handy for debugging. All it does is just terminates the simulation. So it's let's say you have a long XML file and you only want to run it only to a certain point, and then you want the simulation to finish. Then instead of commenting everything else out, then you just put a stop at the place where you want the code to finish. Starfish is the main loop. So whenever Starfish is encountered, the main loop will begin. Particle trace outputs a single particle to a file, so this can be used to create traces of a particle, so you see how particles are bouncing around. Animation is a method for outputting files at some specified interval, and averaging is for data averaging. So once you reach steady state, you might want to run some additional iterations and just kind of get some really nice smooth solution. Okay, all right. So having said that, here's the base command module. After class from all of these different modules have to derive from. And you can see here that it consists of 5 different functions that are kind of listed in a kind of weird order, but there's process, there's init, start, and finish and exit. And of these 5, only the process is an abstract, so all these other ones only have a body that actually does nothing, as you see is empty. But this means that if you're writing some module and you don't actually care about it initializing or doing something at some kind of cleanup, then you can just leave these as they are. You don't have to actually override them. But the process has to be overridden because it's it's abstract, and this process function is what gets called whenever that key of this module gets encountered in the XML file. So again, like here when you'll say see restart in the XML file, then the process function of restart module will be executed. Okay. Now, init and start can be used to initialize the simulation, and finish and exit are used for a cleanup. Now you might be kind of wondering why there's two of them, and so the reason is that you can kind of saw here that we call the init modules, here, and then we call the exit here, but the issue is so the start and the finish. So these get called even before we start processing. So init and exit. Init gets called even before we start processing the XML file. The start gets called at the beginning of the main loop. Okay. So the reason we have two of these is that there could be cases where one module requires some other module to already be loaded. So as an example, for instance, my material interactions module needs to know all the different materials that exist in the simulation, so you can generate some data structures that are needed to kind of handle different surface interaction types. But this information will not be known until we encounter that materials tag in the XML file. So if I try to do this initialization in this init function here, then I would actually have no materials available at that point. So I need to wait for the materials to be loaded in. So I need to wait for the for user to kind of list the materials in the input file. And so having the second initialization function lets me do that, because this will get called just before the main loop begins. And so hopefully by then the materials should be defined. Okay. And just sort of for symmetry, we have this finish function, but I don't think anything actually uses that. So don't feel bad if you don't end up utilizing it. I don't think actually any module uses finish, and exit is used kind of at the end, so you can just maybe close some files or whatever. Okay. All right, so here's just kind of a quick example. This is the node module. So again, this is going back. You already saw this piece of code right here, but this is how it was put in our our map. So just saying that this is the key, it's the string node, and then this is the actual object, this instance of this node module. And so what happens is that when we're processing the XML file, we encounter this XML element, that is called node. Then the process function of this object, this node module, will be called. Okay. And so you see this process function is very simple, just a single one line, and just writes a message to a log file, and is these asterisks, and there's the stuff here in the middle. And what this stuff here is that I forgot to mention that this process function, what it receives is this entire XML element. So here this is just this one line, but there could be more stuff. There could be some child elements. So this will basically receive this entire tree, kind of starting at this root, over here. And there is this class called input parser, which contains a lot of kind of handy functions that you can use to access different parts of this XML structure. And so this get first child simply will return this whatever this text right here in the middle. Okay. So in this case, this is just what we do here. So this get first child will just simply return the Starfish tutorial part 1, and then we just output that with this log.message function. Okay. I kind of mentioned here that this input parser provides these handy accessor methods, and you actually see them here on this next slide. Because now we look at a little bit more complex example, and this is the solver tag. So this is for the solver module. So this is the process function. So when we see have the solver tag here, and here we have this what's called was known as attribute, which is called type, and it has value of Poisson, and also a bunch of these other kind of child elements. Okay, defined here. And you can see how some of these are being referenced here. So here I'm getting this type here by get value. Get value really means get string, so it's maybe not exactly a good name, but get value just returns this as a string, while we have some additional accessors like get int or get double that cast that information to a different data type, to integer, a double, and I think all of these functions take this optional third argument that could be the default value that will be provided in. If there is nothing specified like here, then this will throw an exception. So you need to kind of catch it, because here I'm kind of saying I'm requiring for the user to specify this type, but some of these other things, they don't have to be specified. So these can be just I can just get in some default values here. Okay. And so what I'm going to do on the next slide is I kind of go through this in a little bit more detail because I want to kind of show you again this little bit, object-oriented nature of the code. But so we'll be kind of, looking at this part here. You can see that, here we have the string type, and here we're getting the, just the string value. So just, this just basically type will be equal to Poisson at this point here. And if the, if this type was not found, then we'll just show some error message. And otherwise, we'll call this, we'll try to get something from what's known as a solver factory. So we'll get some kind of solver factory that corresponds to this object. Okay. Now, one thing I forgot to mention is actually kind of very important, is that these accessor methods, these get in, get double, get value, they actually allow you to obtain the data regardless of how it was defined. And here you see that this has type is listed as an attribute, but this doesn't need to be listed this way. This actually could be very easily just be put here. So I could have here this less than type, greater than, and then have Poisson in here, and then just put the closing tag. And similarly, this n0, instead of being listed as the kind of this child element, I could just list it as an attribute. I could simply just have n0 equals 1e12 listed here on the same line. And because these Starfish doesn't actually care how this is defined, so all of these you kind of check both of these options. And so this kind of makes it a little bit easier for the end user, because it's really up to you, how you want to specify things. And the reason I do it this way, just because it makes it, it looks more clear to me, I guess, in a way. This way I can see right away, oh yeah, this is a solver of a type Poisson, so it's kind of, it's more visible in a way. But this is really just, what I like, my convenience. But very easily you could just have it listed here. Okay. So you don't think that just because you see something listed in a certain way in the example files actually has to be listed that way. It could be listed very easily here as a child element. Okay. All right. So here's the what I was kind of discussing, and the big point of this is that Starfish implements all this modularity using object-oriented programming, and you already saw this in a way by seeing how all these different modules inherit from this base the type called command module. And now the solver module is another example how this kind of modularity is implemented. And so the this type that we saw is simply used to retrieve a solver factory from a hash map. So I have this map that contains different factories, and in my init function, that you talked about earlier, we're initializing different modules. Here I'm registering different solvers. But really what these things are, you're simply adding a bunch of different factories to some other map that exists here. So this is a map of different solver factories, and I'm just adding this is the key, and these are the different values. Okay. And so when this type string is read in, I'm just simply looking for a for a key or for a value for that key. So I just make sure that key exists in this map, and then I retrieve back that corresponding solver factory. Okay. But you can see that these solver factories here are some specific types like EF solver factory, Boltzmann solver factory, Poisson solver factory, but these all inherit from this base type called solver factory. So when I'm getting something back here, I'm just getting the base, the top level of the base class. And so at this point, this process function actually has no idea what kind of a solver we are instantiating. All it knows is that this factory will contain a function called makeSolver. So I don't care that whether this factory is constant EF, QM, Poisson, or whatever else. I just know that since it inherits from this base type, or actually is an interface, then it will contain this function called makeSolver. Okay, which I can then call. Which also shows you kind of right away here that one way you could extend the code is by registering additional solvers. Okay, and this is actually what the plugins are very useful for. So we'll now talk about plugins for a little bit, and we'll actually see how this actually could be done. Okay, so again, the easiest way to extend Starfish is using plugins, and this is actually in fact how the full version of Starfish works. It's just a whole bunch of plugins, and I was showing you here. This actually is the full version of the code, and The way I create the full version is actually how I would recommend for you to also modify Starfish to extend it. And that will be by creating a completely new project, new Java project, and you can call it whatever you want to, something like my Starfish extension or whatever. And when you do that, you can add a new dependencies under these libraries. So go to libraries, and you can do add project, and then you can list Starfish-LE as one of the dependencies. Okay. Now, the next thing you need to do is that you'll need to create your own main function. So your project will also contain a main. So now there will be a main defined in Starfish-LE and also one main in your new project. But this actually is not a problem in Java, because in Java, when you try to run a code and there are multiple mains defined, the run command will ask you, hey, I found multiple mains, which one would you like to run? So you just simply have to tell it you want to run the one from your new project. Okay. Or in the case of this full version of Starfish would be, this function right here. And then what your main needs to do, it just simply creates a variable of which is an array list, or which is just to be a list. It doesn't have to array list, it's just to be a list of plugins. And then we populate this list by all these different plugins that we want to add. So this could be whatever you need to do. These plugins are they implement plugin. This actually this is not needed here for this wrapper, but this is actually how you would kind of do it. So you have some class that implements plugin, which means that it needs to implement a function called register, which is the function that will be called by the register plugins function that we saw earlier. Okay. And then within that, you could, for instance, do something like solver module.register solver, my solver factory. And now by doing this, now you magically, you told solver module, now there's a new solver, and now the user could then specify my solver as the solver type in the Starfish XML, and then it will use your solver code to do whatever needs to be done. Okay, so here's an example of the gas dynamics plugin from the full version. So this kind of shows you just how this actually looks like. So again, you have public class and it implements plugin, so it needs to override this register function. And here I'm just kind of adding a bunch of stuff. So materials module, I'm registering new material type of the fluid diffusion, and this is whatever parameters are needed here for that. Interaction module, I'm registering new interaction called of type DSMC, and I'm also registering a new cross-section sigma. Okay, so this is kind of very specific to what modules you are registering stuff for. Okay, all right. Now going back to the solver, in the solver module there's a function called update fields, and this is actually what gets called by the main loop. And the way it looks like is kind of shown here. And so first thing we do, we update the charge density row. And this is a little bit hard-coded for plasma simulations. In gas simulations, you actually wouldn't really care about it, but here I'm just kind of doing it, I guess, for simplicity. And next thing I do is I call an update function on the solver. So again, at no point here do I actually know what my solver is. I just know that since it inherits from this base abstract type class called solver with a capital S, then it will need to define a function called update. So I just simply know that this update function exists, and I'll just call it, and then let the solver do its own magic, whatever it needs to do. And there's also at the end I also update this gradient field. So after I solve some solution, I solve this gradient field, so which is used by some other for instance in case of the PIC simulations, the solver will solve Poisson's equation, so solve for potential for phi, and then the gradient field will then contain the electric field, the gradient of potential. It's kind of not really shown here. I don't think you can see it here. Yeah, I think at some point it needs to be multiplied by -1, so I'm not quite sure how this actually is done here, but maybe the multiplication is done at some later point, because we know the electric field is a negative gradient. Okay. All right. So, and the next thing, so I want to kind of show you is kind of this, the very trivial solver. So this is probably the most trivial solver you can have in the PIC simulations, which is the Boltzmann inversion. Okay. So here we have, we basically just setting the potential phi is equal to some, reference potential phi 0 plus some reference electron temperature KTE 0 times its natural log of Ni over N0. Okay, and so this solver is defined in this qnsolver.java in starfish.pic. Okay, and in this class, in this qnsolver class, I'm creating a new member, new class member called Boltzmann Solver Factory, which is of a type solver module.solver factory. So, this is simply creating a variable, right? So the variable is called this, and this is the type. So this could be, a double, kind of in more simple terms, this would be, a double precision number, for instance, but, here the type is actually the solver module.solver factory, okay? And this is actually an interface. And so to do that, I need to basically flesh it out the way it's shown here. So I just have this new solver module solver factory, and I need to define here this, the body of it. So this is kind of like a one-line way to actually create an interface. So we need to specify this make solver. Every factory needs to have this make solver function defined, and this is what actually is handling the type. So kind of maybe I jump back here, kind of a few lines. So remember here, the only thing we do in our loader, we load in the type of the solver by checking this type variable, and then we just get the factory corresponding to a type, and then we pass the rest of the all the element which will contain all these different things over here to that solver factory, and then allow it to process it as needed. Okay, so this is exactly what we're doing here. So we're getting the element here, and then I'm just getting some some double precision numbers for these parameters that are needed for the reference potential, reference temperature of electrons, and reference plasma density. So I'm just getting these values here, and then I instantiate a new solver of type qnsolver, and just the way this is set up is that the constructor takes as argument these three reference values, but that's just how I wrote this. It doesn't have to be exactly that way, but that's just how it's set up here. And then some logging messages, and finally I return this solver back. And again, since this qnsolver is derived from this base type solver with big S, I'm just returning back the the solver switch of the type solver as opposed to qnsolver. Okay. All right. Now, so that shows you how things are actually instantiated, but now how do we actually solve the potential? And so that's in this update function. So the first thing we do is we need to we loop through all these different meshes. Starfish supports multiple meshes, even though the support is a little bit broken at present, but will be fixed in the future. But for now, just to make things general, you should always loop through all the different meshes because you can have multiple meshes in the simulation. Okay, so each mesh contains a number of nodes in the I direction and number of nodes in the J direction. This is because Starfish is at least for now supports only logically structured meshes, so they don't have to be rectilinear. Like you can have a stretch mesh, but there needs to be a logical kind of topology. So there needs to be a fixed number of nodes in the I direction, fixed number of nodes in the J direction. Now at each node there is a field defined, or there are multiple fields defined, and so fields are really the variables that can be stored on the mesh, and all the fields are of type called field2D. So this object contains some help functions for clearing the data, setting it, and also for doing some gather and scatter, so for interpolating from and to the mesh. And you can also use a get data function to actually get the access to the actual raw two-dimensional array that contains all the actual node values. So in this domain module, when we kind of create a new simulation domain, new simulation mesh, this domain module will create, we kind of automatically create, some common fields, and these include potential. So there's phi and rho, and you can get fields by their name, but there are these sort of a shortcuts. So this get phi will just return back just the potential basically, so you don't have to kind of do a string comparison, because there's a way you could just say, give me a field with a variable that is called something, like a phi, and then you have to kind of go through this kind of list and I guess another map and search for get the appropriate key. So this is just kind of a little bit of a shortcut for doing that. But anyway, so here we get the actual data. So now we have a two-dimensional array of these doubles. So this contains the potential. This is the I index, the J index, and this is the charge density row. Okay. And so the next thing we only have to do at this point is just simple loop to all the nodes. So just loop to all the I's and all the J's, and we first make sure that the node is not a fixed node, it's not a Dirichlet node, because on Dirichlet nodes we don't want to be changing the potential because that's fixed. So we skip those, and all the other ones I just compute my number density by dividing the charge density by the elementary charge, and then as long as the density is non-zero, since we cannot take a log of 0, then I evaluate this function. Otherwise, I just give it some minimal value, just kind of assuming that density is 10 orders of magnitude smaller than the reference. Okay, so that's it. So this is the entire solver. So obviously for Poisson solver, this will be more complex. You have to do some iterations and whatnot, but this right here is really kind of the quick intro to how we can actually access the data on the computational mesh. Okay. All right. So so far we spent, I don't know, 20 minutes, whatever, talking, and we still haven't discussed how to actually how the simulation actually runs. What is the main loop? So this happens in the process function of the Starfish module. So when the Starfish tag is encountered, then the process function will be called, and the one is shown here, and that's in starfish.java. And so what we do here is that we first get some optional values, randomize. You can use to randomize the number generator, and also max processors. There's some rudimentary multi-threading support, so this allows you to how many threads, actually what we call maximum threads, so maximum processors. And so you kind of load this information, but then the main thing is here. So first we start all the modules, so we talked about earlier. Here we're going to loop through all the modules and call the start function. Then I go into my main loop, and when my main loop finishes, then I call the finish on all the modules. So the main loop performs the typical operations that you expect in the PIC or DSMC code. So first, we inject some mass into the simulation domain. This could be either from surface sources or could be from volume sources. Then the densities of different materials are computed at the new step, and this is basically the particle push part in the PIC code. Then the interaction between different materials are considered, so these would be collisions or maybe some chemical reactions. Then we update different fields to compute forces. So for instance, the Poisson's equation could be solved. And then restart data is saved as needed. And then also, we do averaging and file output again as needed. And all this is repeated until some stopping condition is met. And this will typically be some max number of time steps or the simulation reaching a steady state. Okay. So in practice, this is actually what it looks like. So this is the actual main loop in practice. So we start out by printing this message to the screen, and then we restart. We load the restart data from the restart module, and then we compute the initial field, and then I'm using this time module has a function called hasTime, and this will be true as long as there is more simulations, more time steps to be run. So once the simulation finishes, this will return back false. Okay. So here I go to the source module and I call a function called sample sources. And this will, there are multiple different types of sources, and this will, use those to inject material. Then there is the materials module. Then I call update materials on that. Then, here's the perform interactions for interactions module, solver module update fields, and then here's just the restarting stuff and animations and averaging. Here just bring something to a screen. And finally, I advance my time to the new time step. And this will also do things like, for instance, computation of whether the steady state has been reached, and also we'll check whether we actually need to keep running or not. And so once this finishes, then we do check for a steady state, and if it have not reached steady state, then we'll print a warning message to the screen. Okay. So what I want to do now is talk a little bit more about this part here, this update materials. And again, I keep kind of repeating myself a little bit, but this is another example of this kind of modularity that is afforded to you by object-oriented programming. Okay, So, Starfish is mainly used for kinetic simulations, but it's not hardwired to do this. And the main thing to realize is that even in PIC simulations, we actually mainly care about the density, of the different species. We don't actually care about the particles because we need the density in order to compute the Poisson's equations, to compute potential from the Poisson's equation, right? And so this kinetic push of particles is, like new position, like x at time k plus 1 is the all plus, velocity times delta t. It's really only an intermediary step that is needed, that is used to compute this density at k plus 1. Okay. And so Starfish implements this abstraction in the sense that every material implements a function called update, which computes the density, temperature, and bulk velocities at a new time step. Okay. Now we don't actually care about how this computation gets done. So for a kinetic material, so kinetic meaning implemented by particles, this implies pushing the particles forward by delta t. So and then performing the scatter to scatter the, so it basically implies doing this push right here and then doing a scatter to interpolate all these positions to the mesh nodes, so you can compute the number density. For a fluid material, this might imply, for instance, advancing the Navier-Stokes solution, forward by delta t. Or for a maybe diffusion type material, another type of fluid material, this could imply advancing, the diffusion or the advection diffusion equation, forward by delta t and whatnot. But the bottom line is that all we care about in the code is the density, temperature, and the velocities. These are the only things that are kind of globally important. How these get computed is really up to each material, to define for itself. And so the update materials actually just looks like this. So we have this list of materials, and for each material we just call a function called update. So, this is actually, a lot of the code will be here. So for kinetic material, this will be the actual particle push. It will be implemented as this update function. For a fluid, this will look very different. We'll be solving some fluid equations. Another thing I want to mention is the materials interactions. And there this actually is not quite correct. There actually are 4 types of interactions implemented in Starfish, and there are surface impact, chemistry, MCC, and DSMC. Well, I guess it's kind of mentioned here, so the full version adds DSMC. So yeah, so I guess in the full version we have 4 of them. And what these are the surface impact is an interaction of some gas material with a surface. Now at this point, only the kinetic interactions are supported, or at least to a full level. So interaction of fluids with materials is still kind of TBD to be completed. But in general, surface impact is is basically interaction of some some gas interacting with some actually surface with some boundaries. Okay, so an example of this would be, let's say, surface recombination or sputtering. Okay. Now chemistry is a fluid type of interaction. So the only thing that comes to play in a chemistry type of interaction are the densities, or the temperatures, and maybe the velocities of the source and the target, or there could be multiple reactants. So so these are the kind of the bulk, the macroscopic properties. The thing to remember is that we can compute these density fields, for instance, even for kinetic species. So even though this is a fluid type, this means that even kinetic materials can participate in a chemical type of reaction, because we use, as we just talked about in the previous slide, we use the particles to compute the fluid properties, to compute these these bulk properties like density. So we can go from the particles to the the fluid density. MCC is a particle fluid interaction. So in MCC we actually require the source to be of a particle type, to be a kinetic type. Okay, and so this will be example, for instance, ions colliding with some background neutrals, and for instance undergoing a charge exchange collision. Now, so the source needs to be kinetic, but again the target can be either kinetic or could be actually a fluid material, right? And then DSMC is a full-on particle type interaction. So in that case, both the source and the target need to be kinetic materials. Okay. So just to kind of show you how everything works is that, again, in the init function we have we do kind of a couple different things. We register some cross sections, but the one I want to point out here is that we are registering different interactions. And again, all of this should be kind of familiar to you by now. All of these are just simply adding different things to some kind of a map, where this is the key in the map, and this is the what actually handles it, is the value of it. And so these are all some implementations of this surface interaction factory. Okay, and we're also registering some math parsers. You can specify some of these. Some of these sigmas, for instance, as using some math equations. So there's this polynomial parser right now that allows you to basically specify a polynomial equation. Okay, but again, all of these things you see are like this register something. This is all the stuff that could be extended in your plugin. So in your plugin, you could register additional interactions, and that's what you actually saw earlier in the previous slide. They've registered a new interaction of a type DSMC to add the the DSMC collisions. Okay. The stuff we talked about in the previous slide was a little bit of a simplification actually in that way. And the material interactions are actually divided into two categories. So this kind of goes kind of like another higher level of kind of abstraction. So we have surface interactions and we have volume interactions. So surface interaction is the the surface hit that we just talked about, and everything else falls under this volume interaction. So MCC, DSMC, chemistry would all be subclasses of this volume interaction. And the reason they're called this way is because they deal with effects that happen within the computational volume or the computational mesh. So I guess volume being in the 3D sense, when you're doing a 3D simulations, you have kind of basically a volume in which the particles would move. And the surface interaction stuff is currently implemented, as I mentioned, only for the kinetic materials, and is actually processed directly doing the particle pushing stuff. And this is something that will probably be kind of moved out and kind of cleaned up in a future version of the code. But currently, in kinetic material.java, when I'm moving particles, for each particle, I call a function called process boundary, which determines whether the particle left the computational domain or if it hit a surface. And if it hit a surface, that they figure out what is the material of this target of the surface that it hit, and then I'll call the perform surface interaction function on this target material. And so this is just a little bit of the code, what that looks like. You get this list of different interactions defined. They could actually have multiple interactions defined for different pairs. We can, for instance, say that if let's say some xenon hit some let's say stainless steel, you can maybe say that maybe 10% will stick, and then maybe 30% will come off specularly, and the remaining fraction will come off diffusely. So I could actually have a list of different probabilities of different interactions. So this just kind of handles that. There's a lot of other code below this, so you can just kind of take a look to this kinetic material.java and material.java for more information. Okay. The volume interactions are instead handled actually by this perform interactions function, which is called by the main loop. And all this does, it loops through all these, all these interactions that are in this list, and it calls the perform function on them. Okay. Okay. And just as an example of a volume interaction is MCC. Okay, so it's kind of a very simple example. So MCC, as you know, is type of collision where we loop through all the particles, and for each particle we compute the probability from this equation here. It's just 1 minus exponential of the minus of a cross section times the relative velocity times the density of the target and times delta t. Okay, and then this is compared against a random number, and then according to that, we can perform some interaction. So in MCC, again, looping through all the meshes, and in Starfish, a mesh will contain a list of particles. So actually, particles actually live within a mesh, because you can think of a mesh being sort of like a domain in a way, right? And so when a particle moves from one mesh to another one, then it gets kind of sent off to a different mesh. And so in each mesh, I can get this this iterator of particles. This is how I loop through particles, and I can also get this density of the target. So this target is a material, and so I can get the density. So this is just the fill 2D. So this is, the density of this target on this mesh, okay? So this target could be, let's say, xenon neutrals, right? And so here I'm just looping to all the particles, and for each one of them, I evaluate this target density by evaluating this field at the particle location. So this is the gather operation from PIC. And now I sample some random velocity. The problem with MCC is that we don't actually have a target particle. So what I'm doing, I'm just kind of creating like a random kind of virtual particle by just sampling a velocity, and this will sample based on this target temperature or of the cell temperature. And here, there's actually, it's not actually quite right. This actually is missing a step here because I'm supposed to be subtracting my particle velocity from this target velocity. So this is kind of, I guess, missing a line here. And so this should be, the difference between those two. And here I'm just computing my probability, and then, there'll be additional code below this. Okay. So that's it. So this is the MCC implementation in Starfish right there. And that's actually all I had for today. So I know we didn't quite cover everything. That's, for instance, we didn't even discuss the boundaries module or the mesh module, domain module in a lot of detail, but I'm kind of hoping that kind of at least gave you the, maybe the insufficient top-level overview of those functionalities to kind of, get you at least somewhat oriented in the code. But, the best thing is, if you have anything comes up, something's not clear, don't hesitate to contact me. This is my email address right here. And I'm really hoping to make this code, be useful for the community. So, if you find it useful and you want to implement some functionality, if you're not clear on something, shoot me an email, and I'll do my best to help you out with it. Okay. So thank you for watching, and that's all I have for today. And keep an eye on the website for more information. All right. Thank you.